Dear students, welcome to the online class for the subject Power System Analysis and Stability. For stability studies, equal area criterion is the very important parameter. So we will discuss what is mean by equal area criterion and how it will help to stability. So in a system, to determine whether a power system is stable after a disturbance, it is necessary to plot the swing curve. We already seen in the previous video. If this curve shows that the angle between any two machines, so power system will consist of several number of machines, right? Any two machines tends to increase without limit, the system is unstable. If after all disturbances, the angle between the two machines reaches maximum values and thereafter decreasing, so this oscillating with constant amplitude, it is probable although not certain that the system is stable. There is a simple graphical method of determining whether the machines come to rest with respect to each other. So we will compare the two areas, so before the occurrence of the fault and after the occurrence. This method is known as the equal area criterion for stability. The principle by which the stability under transient conditions is determined without solving the swing equation is called the equal area criterion of stability. When this method is used, it completely eliminates the need of computing swing curves and hence saves considerable amount of work. The derivation of the equal area criterion is made for one machine and an infinite bus, although the method can be adopted to two machine systems. Although not applicable to multi-machine systems, the method helps in understanding how certain factors influence the transient stability of any systems. So what are all the assumptions we have to do in performing the equal area criterion? So constant input over the time interval being considered, damping effect is neglected, constant voltage behind transient reactance. We have to assume. In a two-machine system, it is quite likely to be stable if it survives the first swing. So what are all the validity of the assumptions? The assumptions of constancy of the input power is justified by the fact that the effect of the action of governors on the input will not be appreciable up to the first swing. So when the fault occurs, immediate first swing, and thereafter it will only tend to restore stability. The effect of damping would be slightly reduce the amplitude of the first swing and would therefore tend to diminish the amplitude of any subsequent swing. When a fault occurs in a system, the fault current tends to cause demagnetization of the field due to armature reaction, and the field current increases to the extent required to offset this effect so as to keep up the constant flux linkage of the field circuit. If the machine is not provided with a voltage regulator, the field current decreases to its original value as also the flux linkage. As the time constant may be a few seconds during the first swing, there will not be any appreciable decrease in the flux linkage. Now we will move into the derivation part of the equal area criterion. The swing equation of a synchronous machine swinging with respect to an infinite bus is given by m into d square delta divided by dt square is equal to accelerating power Pa minus mechanical input power minus electrical output power, that is P is equal to Pi minus Pu. So we know that, see, d square, when we are bringing these two, that is m d square delta divided by dt square, which is equal to Pa, right? When we are considering only this, d square delta divided by dt square will become Pa divided by m. This multiplication of m will become denominator. This will be considered as equation number 2. So multiplying both sides by 2 into d delta by dt, then 2 into d delta divided by dt, d square delta divided by dt square is equal to 2 Pa by m d delta divided by dt. So this d delta d by dt has been taken outside, and this 2 has been come on to the power d delta divided by dt whole square, that is equal to 2 into Pa by m d delta divided by dt. Then we are removing, that is we are multiplying the dt on both sides. We will be getting d into d delta divided by dt whole square is equal to 2 Pa by m into d delta. So upon integrating, so this differentiation will get cancelled. If once first time we are integrating means this will get cancelled. So d delta divided by dt square is equal to integration of 2 into Pa by m into d delta. So this 2 by m is nothing but constant. We are taking outside. That is 2 by m integration of Pa into d delta. So when we are dividing one more power, then this will become d delta divided by dt. This is equal to root of 2 by m into integration of Pa into d delta. So if d delta divided by dt is nothing but angular velocity omega, the velocity of the displacement angle with respect to the infinite burst, then this omega is equal to d delta divided by dt, that is equal to root of 2 by m integration of Pa into d delta. If the machine is continuously swinging, then above equation will be non-zero. Stability is indicated by zero value. That is, if the integral vanishes, that is integration of Pa into d delta is equal to 0. If this becomes 0, then this will be vanishes. So we are substituting Pa instead of Pi minus Pu. See, we have written here, right? Pa is equal to accelerating power is equal to mechanical input power minus electrical output power. When we are substituting here, that is equal to 0. Then we are multiplying Pa into d delta minus integration of P into d delta is equal to 0. Now we are getting the condition integration of Pi d delta is equal to Pu d delta. Under steady operating conditions, Pi is equal to Pu, that is input mechanical power is equal to output electrical power as given by the constant input line. So the power angle curve has been shown in this figure. So power has been drawn in y-axis and delta angle has been drawn in x-axis. So let us assume that the initial angle delta naught, the corresponding value of Pu is given by the point B. So the corresponding value of Pu has been given in the point B. Bf, so this B to F. For the stability criterion, integration of Pi du is equal to integration of Pu du. So which is indicated by the equality of the area of the rectangle. So this Pi du is nothing but AF GDA. AF GDA, this part, this rectangle part, that is equal to area BCED GFB, BCDE GFB, BCED GFB. So this can be written by two areas, that is area AFGDA has been written as area ABC plus area BCDGF. ABC plus BCDGF. This rectangle part has been written as a combination of two area. One is this shaded portion ABC, the another one is BCDGF. This is equal to area CED plus area BCDGF. Area CED shaded portion and BCDGF. BCD and GF. BCDGF. So now we are, see this area is equal to this area BCDGF, here also area BCDGF. Then almost area ABC is equal to area CED. So A1 is equal to A2, which is shown by the dashed line. That is, the area A1 below PI line is equal to the area A2 above PI line. Below PI line and above PI line. This area is equal to this area. Hence this method is called as equal area criterion. So from the figure, AB represents Pi minus Pu, that is nothing but accelerating power corresponding to the initial angle delta naught. DE represents Pu minus Pi, decelerating power, and when accelerating power is equal to the decelerating power, that is stopping power, the machine tends to return to the original condition if there is balance between the two areas at delta is equal to delta maximum. The system will remain in stable condition only when A2 greater than or equal to A1. That is, if the accelerating area A1 is greater than the decelerating area A2, the system will definitely become unstable. So this is what the condition for equal area criterion.